In this video, we will practice solving related rates problems. That's where you're given one rate and some other information, and you're asked to find another rate. If you appreciate the content, please give it a like. A ladder 13 feet long is leaning against a vertical wall. The base of the ladder slides away from the wall at a constant rate of 2 feet per second. Part A. How fast is the top of the ladder moving down the wall when the base of the ladder is 12 feet from the wall? Include units in your answer. When you introduce new variables, you must define those variables, but you are allowed to define your variables by drawing a picture like this. So, according to this picture, x represents the distance between the base of the ladder and the wall, and y represents the height of the ladder on the wall. This is mandatory. If you don't draw a picture to define your variables, then you have to write it out in words. They gave us a rate, and they're asking us how fast is the top of the ladder moving. So they're asking us for another rate. So we know this is a related rates problem. So we will begin by creating an inventory of facts we are given and what we are looking for. The base of the ladder slides away from the wall at a constant rate of 2 feet per second. Since we called that distance x, we are talking about the rate of change of x, or dx dt. Now this could be 2 or negative 2, and that depends on whether x is increasing or decreasing. If the base of the ladder is sliding away from the wall, then x is increasing. So the rate of change is a positive 2 feet per second. But pay attention to that because sometimes this number will be negative. How fast is the top of the ladder moving when the base of the ladder is 12 feet from the wall? A related rates problem is usually based on a moment in time. And we are being asked about the moment in time when the base is 12 feet from the wall. In other words, at x equals 12, since we defined x as the distance between the base of the ladder and the wall. We should also include what we are being asked to find, which is the rate of change of the top of the ladder. So that's going to be the rate of change of this distance y. In other words, we are looking for dy dt. Now we need some sort of relationship between these variables. We need an equation we can differentiate to make dy dt appear. Hopefully you look at this picture and think, Pythagorean theorem, right? In other words, x squared plus y squared is equal to 13 squared. Let's differentiate both sides of this equation with respect to t to make dy dt appear. Be sure to use the chain rule on each one of these terms. So taking the derivative of the outer function gives me this, and let me go ahead and set up the other one too. The derivative of a constant is going to be 0, but the inner function here is x. So according to the chain rule, we have to then multiply by dx dt, so don't forget that. Notice that the derivative of x is not 1 because we are not taking the derivative with respect to x, it is with respect to t. The inner function here is y, so we multiply by dy dt. We need to find dy dt when x is equal to 12. But don't simply plug in 12 without using proper notation. You have to say at x equals 12 before you plug in the 12. We can also substitute in the fact that dx dt is equal to 2. So I'm noticing that we have everything we need to find dy dt, except we are missing the value of y. This is common that you're going to realize belatedly that you are missing a value. Don't panic. That just means you need to do a little side quest and go off and figure out what that value is. We need to figure out what is the value of y, again, at x equals 12. So even over here in the side quest, let's use proper notation and say at x equals 12. We know the Pythagorean theorem applies, and at x equals 12, that becomes 12 squared plus y squared is equal to 13 squared. That's 144 plus y squared is equal to 169. Whoops. Then subtracting 144 from both sides, we get y squared equals 25. Taking the square root of both sides, y is equal to 5. So at x equals 12, y is equal to 5. Of course, normally when we take the square root of both sides, we do plus or minus, but these are lengths in the real world, and you can't have negative lengths. So y is equal to 5. We can now take that value from the side quest and plug it in and continue. So let's simplify this. 2 times 12 is 24, times 2 is 48. So we have 48 plus 10 dy dt is equal to 0. Subtracting 48 from both sides, I think I'll do it over here, we have 10 dy dt is equal to negative 48. Then if we divide both sides by 10, we get negative 48 over 10, which simplifies to negative 24 over 5. Don't forget the units. This is the change in length divided by the change in time. And the lengths are given in feet. And the time is in seconds. So this will be feet per second for the units. Same setup, part B. The ladder, the vertical wall, and the ground form a right triangle. At what rate is the area of the right triangle changing when the ladder is 12 feet from the wall? Include units in your answer. The same two inventory items that we had in part A still apply. In addition, I've included the two facts that we discovered as we worked our way through part A. At x equals 12, we now know that y is equal to 5, and the solution to part A was that dy dt is equal to negative 24 over 5 at x equals 12. So this is our current inventory. Well, in addition, we need to include what we are now being asked to find. At what rate is the area of the right triangle changing? We are going to need a new variable, capital A, and we must define that variable. So I don't see a way to just do that in the picture, so we have to do it in words. This is mandatory. A equals the area of the right triangle. Therefore, we are being asked to find dA dt when x is equal to 12. We are going to need a relationship that we can differentiate, and it must involve area. So what is the area of this triangle? We know that the formula for the area of a triangle is 1/2 base times height. In this case, the base is x and the height is y. So 1/2 x y. So let's take the derivative of both sides of this equation with respect to t to make dA dt show up. Be careful, we are going to need the product rule. A really common mistake, especially for some reason when it's really simple and we just have x, y. Students really just want to put dx dt times dy dt, you know. So this is a super common mistake. Students will think that this is the derivative of this, but no. This is a product, right? This is x times y. So you have to use the product rule. It's not optional. So let's go ahead and include the 1/2 with the x. So we have the yellow factor and we have the blue factor. So the derivative of the left-hand side is the dA dt that we are looking for. But for the product rule, we sort of go through it twice. The first time through, we take the derivative of the yellow factor. So I'm just going to bring down that constant. But the derivative of x with respect to t is dx dt. The first time through, we leave the second factor unchanged. And then we put a plus and we go through it again. The second time through, we leave the yellow factor, the first factor, unchanged. So 1/2 x. And the second time through, we take the derivative of the second factor, which in this case will be dy dt. So this is an expression for dA dt. We need to find the value of this when x is equal to 12. So we are about to plug in x equals 12 and some other things, but some of these things are only true when x is equal to 12. So you can't just plug them in. You have to first say at x equals 12. Then you can go ahead and plug in all the stuff. This is a full credit answer as long as you include units. This is change in area over change in time. So considering that the units of length are feet, then the units of area will be square feet. And the units of time were seconds? Seconds. So feet squared per second. So this is a full credit answer. Same setup. Part C. How fast is the angle formed by the ladder and the vertical wall changing when the base of the ladder is 12 feet from the wall? Angles are measured in radians. They are talking about the angle between the ladder and the wall. So that's this angle right here. So we need a new variable, and let's use theta, the traditional variable for angles. And let's build out the inventory. This is similar to what we had in parts A and B, but in addition, what we are looking for is the rate of change of this angle. So we are looking for d theta dt. Now we need a relationship between the quantities in this picture and theta, since we are looking for d theta dt. The Pythagorean theorem won't help us this time, because that only involves sides, not angles. So when you are dealing with an angle, the relationships you are going to need are trigonometric. So start thinking about sine, cosine, and tangent. So I don't know if they teach this still, but back when I taught geometry, we used to say SOHCAHTOA sometimes. We just said it all together like that to help us remember that sine equals opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So you need one of these three relationships. I'm going to pick sine theta, and sine is opposite over hypotenuse. Obviously the 13 is the hypotenuse. From the perspective of theta, the side that is opposite theta, meaning across from theta, is this x. So opposite over hypotenuse is x over 13. I'm going to rewrite this slightly before I take the derivative to make it more clear how to differentiate. I'm going to pull the x off to the side. So x over 13 is equivalent to 1 over 13 times x. Now let's take the derivative of both sides with respect to t to make the d theta dt show up. We are going to be doing the chain rule for, well, definitely for this term on the left. I guess technically we don't need the chain rule for the right because it's just an x. So the derivative of the outer function is cosine, right? The derivative of sine is cosine. But then the inner function is theta itself. So we have to multiply by the derivative of theta. So we must multiply by d theta dt, which is great because that's what we are being asked to find, so we really needed that to show up. And then I see we have the constant, so we're just going to bring that down. And then the derivative of x with respect to t is dx dt. I'm looking ahead and I see a little bit of a problem. We are trying to solve for d theta dt. So we need values to plug in for everything else. And we have dx dt, that's 2. So the issue is right here. We do not have the value of theta, and that's not what I'm actually going to use. So I encourage you to don't worry about the value of theta. If we can figure out the value of this entire factor, cosine theta, we can plug that in and we are good to go. But this is going to require a side quest. At x equals 12, what is the value of cosine theta? We know cosine is adjacent over hypotenuse, and from the perspective of theta, this side is opposite, but this side, the side that's close to theta, is adjacent. So adjacent over hypotenuse is y over 13, but at x equals 12, we found that y was 5. So at x equals 13, cosine theta is equal to 5 over 13. We cannot simply plug in the 5 over 13 because cosine theta is not always equal to 5 over 13. It's only at x equals 12. So you have to say that. At x equals 12 only, then we can substitute 5 over 13 for cosine theta. And we are looking for d theta dt. And we have 1 over 13, and dx dt is 2. So really, I'm going to just put 2 over 13. We can cancel out the 5 over 13 by multiplying by the reciprocal. So multiplying both sides by 13 over 5 will move this basically over here, but it will become 13 over 5. These 13s will cancel each other out, leaving d theta dt is equal to 2/5. As long as we include the units, we are done. We are told that the angles are measured in radians and the units of time are seconds. So the units here are radians per second. Example 4. A conical tank has a diameter and a height of 40 feet. If water is leaking out of the tank at a rate of 80 cubic feet per minute, find the rate of change of the water's height when the water is 8 feet deep. Include units in your answer. The volume of a cone is given by V equals 1/3 pi r squared h. We begin by listing the inventory of things we know and what we are trying to find. Water is leaking out of the tank at a rate of 80 cubic feet per minute. This is the rate of change of the volume. So dV dt is 80. Well, is this positive 80 or negative 80? Is this volume increasing or decreasing? Obviously, if the water is leaking out, then the volume is decreasing. So this is a negative rate of change. The moment in time we are working with is when the water is 8 feet deep. But right now we don't have a variable for the height of the water. So we need to define that variable, which you can either do in words or you can do what I'm going to do and just draw it into your picture. Okay, so this I'm going to call h the height of the water. So that means we are talking about the moment in time when h is equal to 8. So in our inventory, we say at h equals 8. Now, what are we being asked to find? The rate of change of the water's height. Okay, so we are being asked to find dH dt. One more time, you must define the variables you are using in the problem. So you can either say it in words and say let h equal the height of the water in the tank, or you can label it in the picture and that counts. Now we need a relationship that involves these variables so we can cause dH dt to show up. Of course, we're going to use the relationship they gave us. Volume is equal to 1/3 pi r squared times h. Looking ahead, I see a problem coming. So I'm going to write some things down, but if you're following along and taking notes, you might want to stop writing because I'm going to wind up erasing everything I'm about to write, but I need to show you what the issue is. If I took the derivative of both sides with the volume in this form, I would have to do the product rule, and that's no big deal, but on the left side we have dV dt. Now on the right side, here comes the product rule. The first time through, we take the derivative of the yellow factor. So I'm going to bring down the 1/3, well, I'm going to put the pi in the numerator. So let's call this constant in the front pi over 3. But I'm going to do the chain rule on the r squared part. So I'm bringing the 2 to the front. But the inner function is the r, and we must multiply by dr dt. So that's the derivative of the yellow factor. The first time through, we leave the blue factor unchanged, and then we put a plus. Then we go through it again. The second time through, we leave the yellow factor unchanged. So pi over 3 r squared. And we multiply by the derivative of the blue factor, which is dH dt. Now here's the issue. We are looking for dH dt. So we need values for all of the other variables. Let's see how many we have. We have dV dt, which is negative 80. So I'm just going to put a check mark on that. We know that h is equal to 8 at a moment in time. So we have that. But we don't have anything else. We don't have r, and we also don't have dr dt. You might think we have r because if the diameter of this cone is 40, then the radius is 20. But we are talking about the volume of the water. So we're not talking about just, the static volume of the container. We are talking about the volume of the water cone. So the radius, the r in this formula, is this little radius right here, not the 20. So we don't have r and we don't have dr dt. And we don't have any way of finding those things. So we would be stuck. The trick is to do a side quest and find an expression for r in terms of h. And we're going to plug that expression back in with a bunch of h's and not r's. So basically we are going to rewrite the volume formula strictly in terms of h with no r's. And then when we take the derivative, it will be much simpler and we will have all of the things that we need. So how do we get this expression for r that involves h? When you see a shape inside of another shape, and this is common when you have water or whatever inside of a container, the water or whatever's in the container takes on a similar shape. So from geometry class, I'm hoping you remember working with similar figures, especially similar triangles. So if you sort of look at half of the cone, we have a big red triangle for the whole container, and then we have this smaller blue triangle from the water cone. So you can set up relationships, equations. Maybe I'll write this down sort of as a formula first. When you have similar triangles, you have a smaller triangle and a bigger triangle. So you can set up an equation in the form small over big equals small over big. In other words, you can make a fraction by dividing a length from the small triangle over the corresponding length from the big triangle and set that equal to a different length from the small triangle over the corresponding length from the big triangle. Remember, r, the radius in the formula, is the radius of the water cone. So let's set up our first small divided by big. R is a length from the small triangle, and the corresponding length on the big triangle is 20. Not 40. A common mistake is for kids to plug in 40 right here, but we are talking about the radius of the circle, so it's 20, not the 40. Anyway, small over big is r over 20. Now we need a different length on the small triangle, and let's use h, right? The h is the vertical part of the small triangle, and that corresponds to the 40, the vertical height of the big triangle. So r over 20 equals h over 40. Multiplying both sides by 20, we get r is equal to 20 over 40, that's 1/2. So r is equal to 1/2 h. So we can substitute this expression in for r. So instead of r, let's put 1/2 h. Let's simplify this as much as possible before we differentiate. Again, I'm going to write this as pi over 3 instead of 1/3 pi. 1/2 squared is 1/4, so that's 1/4 h squared times another h. So multiplying straight across, we have volume is equal to pi over 12, and then h cubed. So that is a much more simple volume formula. Let's go ahead and take the derivative of both sides with respect to t. On the left side, we will have dv dt. Bringing down the constant, and then let's do the chain rule on the right hand side. So it'll be times 3 and squared, but the inner function is h, and we must multiply by dh dt, the derivative of that inner function. And it's a good thing we do, because that's what we are being asked to find. Make sure you say at h equals 8 before you plug anything in. 3 pi over 12 simplifies to pi over 4. And then we have h squared, but h is 8, so that's 64. So we have negative 80 is equal to 64 divided by 4 is 16. So we have 16 pi dh dt. Dividing both sides by 16 pi, we get dh dt is equal to negative 80 over 16 pi. As long as you include units with this answer, this is a full credit answer. This is change in height divided by the change in time. Length is given in feet in this problem, and time is in minutes. So this will be feet per minute. Example 5. A wading pool is in the shape of a triangular prism as shown. The deep end is 4 feet deep. The pool is 30 feet across and 100 feet long from the entrance to the deep end. Part A. If water is being pumped into the pool at a constant rate of 10 cubic feet per minute, how long, in minutes, will it take to fill the pool? Notice they are not asking us for some kind of a rate, so this is probably not going to be a calculus problem. Let's find the volume of the whole pool. The volume of a prism is the area of the base times the height. The base of a prism is the similar shape that's on both ends of the prism. So we have a triangle here in the front, a triangle in the back. These triangles are the bases. So the area of the base is the area of one of these triangles. The area of a triangle is 1/2 base times height, meaning the base of the triangle, which is 100 in this case. So 1/2 base times height is 1/2 100 times 4. So that's the area of the base. Now it's times the height, meaning the height of the prism, not the height of the triangle. The height of a prism will not be 4. It is the distance between the bases. That's what the height of a prism means. So the height in this context is 30. So what do we have? Half of 4 is 2. 2 times 30 is 60. So we have 100 times 60. So that's going to be 60 with 2 extra zeros. So 6,000 cubic feet. I'm thinking of this as a unit conversion problem. I want to convert cubic feet into minutes. So we know that it is 10 cubic feet per minute. So I want to multiply by a fraction involving 10 cubic feet and 1 minute. But the question is, do I put the 10 cubic feet in the numerator or in the denominator? Well, I need to cancel out the cubic feet. So I'm going to put my 10 cubic feet in the denominator and my 1 minute in the numerator. So multiplying straight across and simplifying, the feet cubed, the units, will cancel each other out, leaving behind only minutes. So this part is gone. 6,000 divided by 10 is 600. So 600 minutes. All right, no calculus for that one. Same setup, part B. If water is being pumped into the pool at a constant rate of 10 cubic feet per minute, at what rate in inches per second is the depth of the water changing at the instant when the depth is 2 feet? Before we get started, when you see water inside of a bigger shape, you should automatically be thinking that at some point we are probably going to use similar figures. We have a small shape inside of a bigger shape. But first we list the inventory. Water is being pumped into the pool at a constant rate of 10 cubic feet per minute. This is a change in volume, so dV dt is equal to 10. But is it positive 10 or negative 10? Well, water is being pumped into the pool, so volume is increasing, so it will be a positive 10. So what is the moment in time we are dealing with? When the depth of the water is 2 feet, we do not have a variable for the depth of the water. So we need to create one and define one. We can define the depth of this water, let's call it h, but we can define it by simply including h in the picture like this. So at the moment when h is 2 feet, so let's add that to the inventory at h equals 2. This is mandatory. You must either include the h in your picture or you must write in words, let h equal the height of the water. What are we being asked to find? At what rate is the depth of the water changing? So we are being asked to find dh dt at the moment when h is equal to 2. So that's the inventory. We now need some sort of a formula that we can differentiate that involves these variables. we see that we have volume, so I think we need to set up a formula for volume. Be careful, the volume we are talking about is the volume of the water prism, not the entire pool. So, the volume of a prism is the area of the base times the height. Remember, the area of the base is this triangle. Since the area of a triangle is 1/2 base times height, we are going to need a variable for both of those things. We have the variable h for the height of the triangle, but we do not have a variable for the base of the triangle. So I'm going to either call it x or I could call it b for base. I think I'm going to call it x. So the area of the blue triangle is 1/2 x times h. So the volume of the water prism is the area of the base, and that's what we wrote so far, times the height of the prism. The height of the prism is the distance between the bases. So it is the distance between these triangles. So the height of the prism is 30. That's the same for the whole pool and the height of the water prism. Both are 30. We can simplify this a tiny bit because 1/2 of 30 is 15. So we have 15xh. So looking ahead, if we take the derivative of this, we'd have to do the product rule, but we will have dx dt and we will have dh dt. We do not have dx dt and we have no way of finding dx dt. So that's going to be a problem. That's why we are going to need similar figures, similar triangles. So we need to do a side quest to get rid of the x. So we need to find a relationship between x and h using similar triangles. So remember, it goes small over big equals small over big. On the small triangle, let's write h. The corresponding side of the big triangle is 4. So we have h over 4. And that will equal another small over big. So another side of the small triangle is x. And the corresponding side on the big triangle is 100. Okay, so small over big equals small over big. We want to substitute for x, so we need to get x by itself so we can substitute that expression back in. Multiplying both sides by 100, we would have 100 h over 4 is equal to x. But, 100 divided by 4 is 25. So that's 25h is equal to x. So we can substitute 25h instead of x right here in the volume formula. So we have volume is equal to 15 and then 25h and then times h. So the volume is 375 h squared. Now we can take the derivative of both sides with respect to t. On the left side we have dv dt. And on the right side we are going to use the chain rule. 2 times 375 is 750. So that's the outer function. But the inner function is the h itself. The chain rule demands that we then multiply by the derivative of the inner function, which is dh dt. The value of dh dt we are about to find is only the value at h equals 2. So you have to say that before you plug in the 2. dv dt is 10. And then we have 750 times 2 times dH dt. Dividing both sides by 750 times 2, to be clear, we could slap some units on here and be done. But when you divide by 10, it's going to cancel out this 0. So we might as well simplify. It's so easy. dH dt is equal to 1 over 75 times 2. And 75 times 2 is 150. The units of length were in feet and the units of time were in minutes. So it's 1 over 150 feet per minute. So on the AP exam or on your unit test, this would probably be the answer. But whoever wrote this question was extra mean, and they said in parentheses they wanted inches per second. So that's just an annoying extra step that we need to do our unit conversion to turn feet per minute into inches per second. To convert feet into inches, we multiply by 12 inches over 1 foot. That will cancel out the feet. To convert minutes into seconds, we multiply by 1 minute over 60 seconds. That will cancel out the units of minutes. So we just need to simplify this down. Actually, you could leave it like this as long as you put the units on there. However, 12 goes into 60 5 times, and 150 times 5 is 750. So dH dt is 1 over 750 inches per second. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.